Section 21.7 Base Hydrolysis. Ligand substitution in octahedral complexes can be greatly accelerated by the existence of hydroxide ions in the solution. When ligands with acidic protons such as ammonia or water are present in the complex. This is because the hydroxide ions in the solution may help convert the ammonia ligand to the NH2- ligand, or the water ligand to the hydroxyl ligand. The NH2- ligand and OH- ligand are better sigma donors than their neutral counterpart. And this NH2- OH- ligands can better stabilize the transition state of the rate limiting step of the ligand substitution in this octahedral complex. When the hydroxide minus in solution convert a ammonia ligand or water ligand to NH2- or OH-, the charge of the complex is decreased by 1. When a ligand loses a proton to this hydroxide in the solution, the deprotonated ligand, such as NH2- or OH-, is a better sigma donor than NH3 or water, and thus this deprotonated ligand is able to stabilize the transition state of the rate limiting step of the ligand substitution reaction. Now let's look at one example. In this reaction between this hydroxide and this pentamine chlorido cobalt 3, this OH- exists in a solution. It serves as the entering ligand, replacing chlorido, but at the same time, the abundance of OH- in the solution helps stabilize the transition state of the rate limiting step of this ligand substitution by removing a proton from one of the 5 amine ligands. So the actual mechanism involves 3 steps. Step 1, this OH- hydroxide ions in the solution may remove a proton from one of the amine ligands. So out of these 5 amine ligands, one of them becomes NH2-, and this NH2- is a much better sigma donor and can donate the lone pair electrons. NH2- has 2 lone pairs, so it's going to use 1 lone pair to form a sigma bond with this cobalt center. The overall charge decreases from 2+ to 1+ because of this change. And because this NH2- is a much better sigma donor than ammonia, it can help stabilize the transition state of this rate limiting step. In this rate limiting step, this chlorido leaves this cobalt center, and now we name this chloride in the solution. So now this cobalt forms 5 bonds with 5 ligands, 1 fewer bond But yet, this step is accelerated because of the stabilization due to this NH2 minus ligand being a really good sigma donor ligand. Alright, so this is the rate limiting step in the 3-step mechanism. And this step is accelerated due to the fact that NH2 minus is a better sigma donor ligand. And then this is a faster step. Water comes in and form a OH minus ligand, hydroxyl ligand, bonded to this cobalt center. What about this NH2? When this water approaches this cobalt center, it gives a proton to this NH2. Now it becomes a ammonia again. Meanwhile, the OH part of water forms a sigma bond with the cobalt. So if you look at this case, the charge of the transition metal complex becomes 2+ again. So from 2+ to 2+. The overall effect is this hydroxyl ligand replaces the chloride ligand. Alright, that's the overall effect. But it's not that this OH minus just come in, form, say, partial bond with cobalt, and this chloride leaves. It's not that simple. It involves the formation of a NH2 minus ligand in the middle. And that helps to accelerate this slowest step in this mechanism. Okay? And this step is dissociation. You go from one particle on the left-hand side to 2 particles on the right-hand side. It's dissociatively activated. The mechanism is dissociatively activated because this step, the dissociation step, is the slowest step. Okay? But the formation of this NH2 minus ligand help accelerate this slowest step. Only because this NH2 minus is a much stronger Lewis base and also much better sigma donor than ammonia.